find the equation of the line of intersection and the angle between the planes 2x minus y plus 3z is equal to 2 and 4x plus 2y minus z is equal to 4. If we have a look at these here we have those planes drawn on GeoGebra. We can have a look at them from different angles, and what we see is that they actually intersect on a line, this line here, from here to here. What we should do is write them in their normal vector form, and if you do that you can see where they're normals. So have a closer look at this, and the angle between the planes is the same as the angle between the two normals. This is because the two normals are perpendicular to each of their planes. So let's have a look at this. You can have a look, see a bit better here. You can see here we have the normal of the green plane, the first one, and I think here you can see we've got the normal of the second plane, and the angle between the planes will be the same as the angle between the normals. Now, in order to find the line, for a line in 3D we need to know one point on the line and a vector which is parallel to the line. Now, to find the vector, what we need to do is we'll need to find the cross product of the two normals. Let's just move it so we can see. So what we can find is the cross product so we can find the cross product, this vector here, such that this angle is 90 and this angle is 90 degrees, and this will be the vector v, the directional vector of the line. And then what we could do is put one of the coordinates equal to 0 in order to find the point, because we need a point and a vector parallel to the line. So there's the diagram which I just drawn. Okay, so first of all, take the equations of the planes and write them in the normal vector form. So the first one is, remember we use capital pi for a plane, so 2x minus y plus 3z is equal to 2. Remember this, the 2, the minus 1 and the 3 gives you the normal vector, so it's r dot 2 minus 1, 3 is equal to 2. This gives you the first normal. So here it is, the green one is that one, and this is the normal vector to that green plane. The second one, plane 2, is 4x plus 2y minus z is equal to 4. And therefore r dot 4, 2 minus 1 will give you equal to 4. That's the orange. This is N2, this is the orange plane here, you can just see. And we've got the normal vector of that plane, which is this one here, is going to be 4, 2 minus 1. Now we've got we need to find this vector here, which will be the cross product of, or the vector product of M1 and N2, because that is the geometrical definition of the cross product, or the vector product is it gives a vector perpendicular to two other vectors. So two planes intersect on a line with a directional vector of v, which is going to be the vector product of m1 times n2, and then the only other thing we need to do is predict one point on the line. In fact, that's the one we're going to find. Right, there's another way of looking at it. Here we have the directional vector, here we have two normals, and we need to find the cross product of these two vectors, or the vector product, which will give this vector here. And this angle here is the same as the angle between the two planes. So m1 is 2 minus 1, 3, n2 is 4, 2 minus 1. We need to find the cross product of n1, or vector product of m1, n2. Remember, we set up I, j, k, and we use determinant method. Write down the first vector, 2 minus 1, 3, 2 minus 1, 3. Write down the second vector, 4, 2 minus 1. And what we do is we cross off this one and then find the determinant of what's left. So we're going to do minus 1 times minus 1, minus 3 times 2, lots of I. Next one's always minus, remember. Covering up the j, we're going to do 2 times minus 1, minus 3 times 4, lots of j. And then covering up k, we're going to do 2 times 2, minus 1 times 4, lots of k. That comes down to being 1 minus 6i, minus 2 minus 12j, and 4 plus 4k. So it's going to give me minus 5i, plus 14, so be careful with the sign, plus 8k. Writing it as a column vector, we get minus 5, 14, and 8. We now have to find a common point. So put z is equal to 0 in both planes, and you'll be left with 2x minus y is equal to 2, and 4x plus 2y is equal to 4. Somewhere we just put one of the coordinates equal to 0 and solve for what's left. Then we only need to find a point. So if I take 1, multiply it by 2, and add 2, that's going to give me 8x, no y's, is equal to 8, and x is equal to 1. And if x is equal to 1, we can very, very easily see that y has to be equal to 0. So the line passes through the point 1, 0, 0, and therefore the vector equation will be r is equal to 1, 0, 0, the point, plus the directional vector, which I found from the cross product, minus 5, 14, 8, or in Cartesian form, x minus 1 divided by minus 5, y divided by 14 is equal to z divided by 8. In order to find the angle between the planes, you need to find the angle between the two normal vectors. So to do that, we're going to use the scalar product. So m1 and n2, this is m1, this is n2 from memory, and then we know that cos theta is going to be n1 dot n2 divided by the magnitude of m1 times the magnitude of n2. So cos theta is going to be 2 times 4 plus minus 1 times 2 plus 3 times minus 1 divided by the magnitude of this one, so it's the square root of 2 squared plus minus 1 squared plus 3 squared, times the magnitude of this one, it's going to be the square root of 4 squared plus 2 squared plus minus 1 squared. On the top we're going to get cos of minus 1 of 3 divided by root 14 times root 19. On a calculator, that gives an answer of 79.4 degrees. Going back to look at this, try and move this. There we can see our line, and there we can see our angle. And if I move this around a bit, we can see, it's probably the best depth view you can get is that one, that this is the angle there, 79.9, and this line from here to here is given by this vector equation.